So, at this point, you should have watched a little YouTube video and recorded the distance that the little boy dropped before Superman was able to catch him. All right. And we're going to use this cinema accurate film to calculate the height of Niagara Falls. All right. First of all, you can make a little sketch. So here's Niagara Falls. All right. And then there's a little boy falling off. And then Superman's going to come and catch him. Ooh. All right. So, what we want to know is, given the time it took for him to drop, what is the actual height? Okay. All right. So, list data with symbol and unit. So in the first video, we talked about filling out a little data table with VI, VF, D, A, and T, and putting in as much information as you possibly can. Now, here's the intimidating thing about freefall problems. Everything can be figured out from one piece of data, all right, because all the other data tends to be hidden in some way. So we can use the same procedure for any kind of dropped object, all right? You should have gotten the time from the video, and the time, it's going to vary a little bit, but let's use a time of about 28 seconds that it took Superman to catch the little boy, okay? Now, you might remember from the first video that you need 3 pieces of data. We're going to be using one of these formulas for accelerated motion. In every single one of them, you need at least 3 pieces of data to find the rest, okay? Again, reminder, these are also on your reference tables right here, okay? All right, and we only have one. That's the first thing that's intimidating about freefall, but that's because the rest of the data tends to be hidden, okay? Now, when the boy falls, he might have had a little bit of sideways velocity, but he certainly didn't have any downward. He wasn't pushing down. So the first one is looking for keywords like stopped, rest. Another one is dropped or fell. All of these tell you a piece of key data, and the initial speed, therefore, is 0, okay? The next thing is that because we're on the Earth and within 17 kilometers of Earth's surface, everything falls at the same rate, and that rate is 9.8 meters per second squared. And that's equivalent to 32 feet per second squared in the English system. Now, if we're going to say that downward is our negative direction, it is important that we make this negative as well, because the acceleration is down, gravity pulls down, it's getting faster in the downward direction. Now we have our 3 pieces of data, and we can actually find the height, which is our unknown here. Okay, so we need to pick a formula that has these things in it and nothing else, all right? So that formula is going to be this one right here, D equals VIT plus 1/2 AT squared. So I'm going to go ahead and pick a formula. All right, move this down a little bit. That one better. All right. Okay. Move this down a little bit. Okay, so the formula is D equals VIT plus 1/2 AT squared. Now, since VI is 0 and 0 times anything is 0, this whole term drops out. And you get what this is called a working formula, D equals 1/2 AT squared. Either one of these would be fine to put on a quiz or a test as your formula with no numbers in it. You could also rearrange this if you wanted to, but we don't need to because we're looking for D. All right, so let's go in and plug in with units. So D equals 1/2 negative 9.81 T squared. Oh, this is a good time to remind you where this negative 9.81 is. Right on the front of your reference tables, we have all of the constants. And on the front of the very first constant on your reference tables is the acceleration due to gravity. And of course, I can't find it right in front of me, so you'll just have to take my word for it. All right. So let's go ahead and solve this. All right. I didn't put the time in. Let's do that. All right. Thank goodness for erasable pens. 28 seconds. Don't forget to square. All right. Our order of operations says we need to square the 28 first. All right, so I'm going to go 28. I'm going to square it. And then, so this becomes D equals 1/2 times negative 9.8. I'm going to drop units times 784. All right. And we get that the height is 3,845.5 meters. All right. I guess we substituted in starting about there. And here's my correct answer with units. And I'm going to go ahead and put a box around that. Now, this comes out to be negative, which shouldn't be surprising since its actual displacement, its change in possession, is a drop down this way. All right. So there is the actual height of Niagara Falls. Next time I'll ask what the real height is. All right.